All right, so we have introduced both the vorticity and the circulation. Those are mathematically very different. The vorticity is a vector field, and the circulation is a scalar, so it's a number which you can define and compute once you've defined a closed contour. But of course, the two are related. That's why we're discussing them at the same time. And so now we're going to discuss the connection between vorticity and circulation. And the two are linked through a mathematical theorem, which is called the Stokes theorem. So let's consider again our flow. And let's say that we are picking a particular contour. So this is going to be our contour here. So we can define the circulation on this contour. We've discussed that before. So along this contour C, if I take the line integral of the velocity field along this contour C, so I'm integrating along C the dot product between the velocity field and the differential element of displacement, I get the circulation. And from Stokes' theorem, we have that this is also equal to another integral, but this time a surface integral, a little bit like when we applied the divergence theorem, and we had that the flux of a vector field through a closed surface was equal to the volumetric integral of the divergence of this velocity field. So here we have that the line integral along this contour C, you can express it in terms of a volume integral, of a surface integral, but first you have to define a surface which is attached to your contour. So we have a contour, and so we can define a surface. So you have to think about this as a little bit as the net that you would have in a or you can think of this as a hat. So this is the rim of your hat, and this is the surface. So it's an open surface because it has two sides. You have one side here. You can go to the surface from this side, and then you can go out and back onto the other side of the surface through this side. So it's not a closed surface like what we were discussing before. It's an open surface. Let me call this surface here S. In that case, from Stokes' theorem, we know that the line integral of the velocity field is equal to the flux of the curl of the velocity field through the open surface. And the way you write this mathematically is it's going to be an integral over the surface S of the flux. So you will have a dot n ds, right? And it's the flux of which vector field is the flux of the curl of u. This here is the Stokes theorem. So that here represents the flux of the curl of the velocity, or the flux of the vorticity field. So we can also directly write it as gamma can also be writing through the Stokes theorem if you have defined a contour C as the flux of the velocity of the vorticity field through a surface S. Now this surface S, you may see that we have relative freedom also about how we choose this surface S, right? So we can take this hat form here, we could take another hat form here, or we could just take the surface, the flat surface here, which is attached to C. And in principle, we always get the same results, right? So that's mathematics. So if we take again our previous example of our shear flow, so here we have a simple shear flow, and we wanted to compute the circulation on this contour, right? So formally in the past section we've computed the line integral, but what we can also do is to use Stokes' theorem to compute the circulation. So from Stokes' theorem I could write that this line integral is equal to the double integral along a surface S of the flux of my vorticity vector. Now we computed the vorticity vector before. We know that our vorticity vector is equal to 0, 0 minus gamma, right? So here we have a 2D flow. We have a 2D flow, but the vorticity is a vector field, and our vector is pointing in the z direction, right? So in the direction coming out of the board. So it's pointing in the z direction. So we have here x, we have here y, and we have z. And now in that case, you have to think about this contour in 3D, right? The simplest surface which we could so what we can do here is take as a surface, simply you have to imagine this contour in 3D. We can use as a surface the surface which is attached to this contour, right? So if you represented it in 3D, right, that would be x, y. This is our contour, and we take this here as our surface, and you see that the normal to our surface then is the unit vector z. Right, so if we take this, then n is our unit vector, n is our differential element of surface is simply dx dy. Right, so we have n, which is z, omega, the vorticity vector, which is minus gamma z. It's independent on x and y. ds is dx dy, and we integrate over the surface, right? So this is equal to the integral over the surface of minus gamma times dx dy. This is a constant, so we will integrate the surface, we just get the surface area. And what is this surface area equal to? It is delta x times delta y, and therefore we find circulation, which is gamma minus gamma times delta x delta y, which is the same as what we obtained when we computed the circulation with the line integral.